Okay, last class of the week. Hopefully things are going on well. Once again, I'm recording all three videos. Um, remember, you can always reach out by email, and certainly within that day, I will give you a reply. But obviously, if it's during school time, I won't do it until I get home. All right, so 8.1 dealt with geometric mean and those three patterns. We'll review that here in just a second. So we're on to more things involving right triangles. And like I said in last classes, the stuff at 8.1 is in 8.1, and we don't see it again until the chapter test. So it's critical that you have those patterns, your understanding of those patterns, and it's in your book of truth so you can use that when we get to the test day. All right, here's your homework. I'm going to repeat myself a lot for these first couple videos. Make sure you pause the video because I'm moving on. So, Pythagorean theorem. Hopefully, this is not your first encounter with the Pythagorean theorem. If it is, you're going to like this. So, last class, we dealt with this particular pattern. Now, it dealt with a right triangle. Today, we'll be dealing with right triangles. In fact, the whole chapter with right triangles. And we get those three patterns. And the three patterns either deal with the altitude. The altitude is equal to the square root of the two pieces of the hypotenuse. It deals with the short leg of the big triangle there. The short leg is equal to the square root of the entire hypotenuse and that little piece there that's on the same side as the short leg. And then lastly, the longer leg is equal to the square root of the hypotenuse again times that piece there that's on the same side as the longer leg. So those are the patterns, and that's what we did last night or the previous one. Cool. All right, so great. We can find the links of the sides of a right triangle. Well, the but here is that when most people think about right triangles, they instead think of the Pythagorean theorem. It's the more, I don't know if popular is the right word, but it's the more common use. When you get into higher level math, especially pre-calculus and calculus, Pythagorean theorem is used quite frequently. This is my favorite proof in all of geometry, or that we do this year, I should say. So I'm going to prove the Pythagorean theorem. And like I said, I'm assuming that you've seen the Pythagorean theorem before. If not, well, then here we go. There's lots of proofs for the Pythagorean theorem. Lots and lots and lots of proofs, but this is a pretty cool one. Okay, so I need to be given a right triangle, and I need to prove that the sum of the square of the two legs is equal to the square of the hypotenuse. And that's where the classic a squared plus b squared equals c squared. So there's the picture right there. C's on the bottom, that's the hypotenuse, and a and b are the two legs of the right triangle. So once again, the sum, that means addition, of the squares of the two legs, that means a and b, so a squared plus b squared, is equal to the square of the hypotenuse. So that's what I'm about to prove. All right, cool. So here's how it's done. I'm going to make the same picture that we had yesterday. So the only thing missing from this picture from yesterday is that altitude. So when I make that altitude, it cuts the hypotenuse C up into two pieces, and I'm going to name those two pieces D and E. Okay, so that's just a basic construction. All right, so since it is now the construction that we used from yesterday, I can say the following. So that means that A, well, see, where is A? A is the short leg, and we know that from yesterday's that A is equal to the square root of, let's see, C times E. Now, technically, I'm going to write that as a squared is equal to c times e. So I'm squaring both sides of that equation from yesterday. Remember, yesterday we would have said that a is equal to the square root of c times e. So if we square both sides of that, I would get a squared is equal to c times e. In other words, it gets rid of the square root. Same thing for b. Technically, from yesterday, b is equal to the square root of c times d. I'm going to square both sides, so I get the statement d squared is equal to c times d. So that's corollary 2 to 8.1, and I kind of left this one off. I squared both sides. All right, if you need to rewind that to listen through that again, please do that. Now, why did I just do that? Well, if we look at what we're trying to prove, we're supposed to prove that a squared plus b squared equals something. And now my two statements say I got an a squared and I got a b squared. So I could add these two equations together. If I add these two equations together, I would get a squared plus b squared is equal to c times e plus c times d. Yay. I just added. Now notice on the right side of that equation, both terms have a c in there. So I'm going to factor out a c. In other words, by division, I'm going to pull out a c. So if I pull out a c, I'm left with e plus d, right? So I mean, it's just factoring. Now look at what e and d are. E and d are the hypotenuse. E plus d is equal to c. So that means I can replace that e plus d in parentheses with another c. That's just substitution, right? Or you could say the segment addition postulate. Well, c times c is c squared, and we're done. I just multiplied c times c. Wow, that's pretty slick. Now, how come this was not proved to you back in, pre-algebra or before when you had Pythagorean theorem? Well, because in order to prove this one, I used the thing that we just did yesterday. So it's not that the Pythagorean theorem can't be proven to you in earlier grades. It's just really challenging. I know when I teach Pythagorean theorem in 7th and 8th grade, I show them a visual proof. It doesn't actually necessarily rigorously prove it. This one does, but they're not ready for rigorous proofs at that age level. You may have seen a proof before where they make literal squares out of the three legs. I find this proof a bit more enjoyable. Okay, so let's write this down in our book of truth. And the Pythagorean theorem says, in a right triangle, the sum of the squares of the legs, that means square both legs, A and B, sum means add, is equal to the square of the hypotenuse. All right, if you need to pause this, I'm moving on. Okay, recall that the side opposite the right angle is called the hypotenuse, and the other two sides are called the legs. So this is where the Pythagorean theorem gets that verbiage from, that the sum of the square of the two legs is equal to the square of the hypotenuse. All right. So how do you apply this to with numbers? How do you apply the Pythagorean theorem to a triangle with numbers? Well, they give you two of the three sides, and you solve for the third one using the Pythagorean theorem. So the only thing is you need to make sure which one is C. That's the critical part. So let's see. C is, in this case, C is our X value. Oh, that's confusing. How come they don't use C? Well, because they can use any variable. So we know that the side opposite the right angle is the hypotenuse, in this case, X. So that side squared is equal to the sum of the squares of the two legs. Well, the two legs there are 3 and 7. So even though we're using the letters A, B, and C, and our example uses X, you just need to figure out which letter goes with which letter of the Pythagorean theorem. So X goes with C, so all I'm replacing is that C with the letter X. And then I'm just going to do the math, and this comes literally from that algebra review solving equations. 3 squared is 9, 7 squared is 49, 49 plus 9 is 58. The square root of 58, are there any perfect squares? This one's a little bit more challenging. 4 goes into 60, so no. 16, no, because 4 goes into 16, therefore it had to go into 58. Bottom line, there's no perfect squares in 58. All right, can this look a little bit ugly? Will they give you some ugly values? They sure will. Look, hypotenuse there is the square root of 58. They say calculate the unknown side. Well, the unknown side is the short leg there, so what do you call it? You're free to call it any variable you want, but we know that the square root of 58 is the hypotenuse. So I generally just use X. You can use whatever letter you'd like. So let's see, the two legs, the sum of the square of the two legs there are X and 7. So X squared plus 7 squared, those would be your A and B, is equal to the square of the hypotenuse, in this case, the square root of 58. So we have to square that, though. We have to square all three sides. 7 squared would be 49. Ooh, from that lesson of algebra root, you know that if you square a square root, the square and the square root cancel each other, and you're just left with the radicand. In other words, 58. Inverse operations, remember? Subtract 49 from both sides. That leaves us, a nice, friendly, perfect square number 9. Take the square root of both sides, you get 3. Okay, so for Pythagorean theorem, you're either solving for a hypotenuse or you're solving for legs. Squaring for the hypotenuse or the legs, the math is very similar. Not exactly the same, but very similar. The last step will always be taking the square root of both sides. All right, so how do we make that? And by the way, that's what you would normally see in an 8th grade class. So how do we make this more challenging? So we're simply going to add some more variables. In fact, we're going to make it way more complicated, is we're going to have to actually solve a quadratic. So a quick review on solving quadratics. We've done this before earlier in the book. So if you have a quadratic equation, remember those are fancy words for I got an x to the second power and it's an equation, then our first step is to make sure you set the equation equal to 0. So notice the equation there on the right set equal to 0. The one on the left, these are two different examples. The one there on the left there, it doesn't equal 0. So step number 1, make it equal 0. In other words, move that -4 to the other side. So if we add 4 to both sides on the left equation there, now it says equals 0. And the only technique that we have so far of solving a quadratic equation is to factor it. So if you remember, okay, this is reaching back, to factor it, we're looking for two numbers that multiply to 12. This is the factoring process. Two numbers to multiply to 12 to add to 7. On the right one there, two numbers multiply to -15 that add to -2. So we'll do the left one first. So two numbers multiply to 12, that would be 1 and 12, 2 and 6, or 4 and 3. Of those combinations, which ones add to 7? Well, the 4 and the 3. So a +4 and a +3 multiply to 12, and they add to 7. Remember how we write this? Parentheses, 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 throw in the variable, and then throw in those two numbers, +4, +3. We use the process called the zero product property. If two things are being multiplied together, look, that's one set of parentheses times another set of parentheses. And if it equals 0, the only way that happens if one of them is 0 or they're both equal to 0. So we set both of them equal to 0 and we solve. Subtract 4 from both sides, subtract 3 from both sides. So we get -4 and -3 are the two answers. On the one there on the right, two numbers multiplied to -15. Let's see, -1 times 15, or 1 times -15, or 3 times -5, or 5 times -3. Of those two, which one add to -2? That's a -5 and a +3. So that would be x minus 5, x plus 3. Once again, we have two parentheses being multiplied together equals 0. That either means the left one is equal to 0 or the right one, or they're both equal to 0. So we set them both equal to 0 and we solve. Add 5 to both sides, subtract 3 from both sides, so -3 and +5. Why are we doing this? Because the triangle that we're about to solve will wind up with a quadratic equation that we have to factor to solve. So, one more time. How do you solve quadratics? Make sure that they're both equal to 0. Both, or set the equation equals to 0. There we go. So on the left one there, we got to do a little bit of work. Subtract 20 from both sides. 56 minus 20 is, what did I just, oh, I see. Never mind. The one on the left there, notice they all can be divided by 2. You could subtract 20 from both sides first, you get the same answer. But in this case, I'm going to divide both sides, everything there by 2, because everything's divisible by 2. So if we divide everything by 2, we would get x squared plus 11x plus 28 is equal to 10. Now subtract the 10 from both sides. Would we have gotten the same answer if we had subtracted 20 from both sides first? Yeah, we would have gotten a 36, and 36 divided by 2 is still 18. So either way would have worked there. Okay. Let's see, we need two numbers multiplied to 18 to add to 11. Let's see, 1 and 18, no. 2 and 9, yeah, 2 and 9. 2 plus 9 is 11. So x plus 2, x plus 9. Set both of those equal to 0, solve, and we would get -2 and -9. Okay, the one on the right there, two numbers that multiply to -20 to add to 1, or to add to a +1. Remember, there's always a 1 in front of any variable. 1 and 20, or 1 and -20, no. 2 and -10, no. Oh yeah, 4 and 5 gets me to 20, but we got to get to -20. So either -4 and 5 or 4 and -5. Which one adds to +1? The 5 has to be bigger. So +5 and a -4. Set both those equal to 0, solve. So we get a -5 and a +4. All right, so that's your quick review on solving quadratics. That seems to come out of nowhere, right? We did that 3 or 4 chapters ago. Now it rears its ugly head. So thank you for reminding me of a painful part of your life last year. Excuse me, but we're going to use that now to solve big kid problems. So here's your triangle. Here's your triangle. So it says solve for the unknown side. Well, we got two unknown sides. We got an x plus 2 on one side and an x. Well, we're still going to use the Pythagorean theorem to solve this. So let's see, the sum of the squares of the two legs is equal to the square of the hypotenuse. The hypotenuse here is 10. So let's see, I got to square both sides. I got to square A and B. A is x plus 2 and B is x. So let's see, I got an x plus 2 squared and I got an x squared. This one's really ugly. So let's see, x plus 2 squared. That's not x squared plus 4. That's x plus 2 times x plus 2. So we probably need some scratch work. Remember, x plus 2 times x plus 2, either using a distributive property or the stacking method, will be x squared plus 4x plus 4. Remember, x times x is x squared, x times 2 is 2x, 2 times x is 2x, and 2 times 2 is 4. When you group all those together, you get x squared plus 4x plus 4. We still got that other x squared. So if we group that together, we see we got 2x squared plus 4x plus 4. And if you subtract the 100 to the other side, 100 minus, I'm sorry, 4 minus 100 will be negative 96. Look, they're all divisible by 2. So divide everything by 2. So we get x squared plus 2x minus 48. All right, now we're in more familiar territory. Two numbers multiplied to negative 48, they add to 2. So it's definitely not 1 and 48 or 2 and 24. 3 and 16, nope. 4 and 12, nope. 5 doesn't go into 48. 6 goes into, oh yeah, 6 and 8. Ooh, that would get me to a 2. So we need a negative 48. So one of them's got to be negative and one's got to be positive. So I'm thinking positive 8 and negative 6. Positive 8 and negative 6. Therefore, the two answers are negative 8 and positive 6. And welcome to geometry. Even though in algebra we can get two answers, in geometry there's only one number there that actually works. Think about this. We're claiming that x could be negative 8. That means one side length there is negative 8. So what you've now encountered is what's called an extraneous solution. That means you get an answer that works algebraically to the equation, but it doesn't work geometrically because we can't have a side length that's negative 8. How about the 6? Sure, the side could be 6 and the other side 6 plus 2 is 8. So 6 is the only answer there for x. All right, so that might be the first time you've ever encountered an extraneous solution, something that works algebraically, doesn't work geometrically. So always be on the lookout for that in geometry. Even it's not that the answer can't be x can be negative, but it's got to make sure that it fits into the problem here. So for instance, if those two sides were like, I don't know, x plus 10 and x plus 12 or something like that, we could get negative 8 for x there. But in this case, because one side is literally just x, I mean, it doesn't matter either side there. It can't be negative 8. You get negative 8 on one side, negative 6 on the other side. Negative 8 plus 2 is negative 6. So that doesn't work. All right, so pretty quick lesson today. It's just the Pythagorean theorem. Remember, this is your homework. If you encounter any problems, send me an email. I'd be happy. And that ends it for the week. Definitely at the end of this, I'm expecting let's hammer out specifically what days we want to meet online and Zoom meeting. I'll be asking you just a couple questions. Don't worry about it. Like it's not going to be a test or something like that. I just want to make sure that you're tracking and you got the understanding of the material. So I'll have some problems for you to, talk me through of how you would solve that sort of thing. We'll meet for, 30 minutes or less each time, or as much time as you need actually, but no more than like say 30 minutes. And hopefully this is working out. If not, give me any suggestions that would help you understand the material more, like could you do this in your videos, more, whatever it is that would help, and I'd be more than happy to do that for you. So have a great weekend, and I will see you next week.